Welcome to SS2 Chemistry, Term 2, Week 6. Many chemical reactions are reversible. They can proceed in both the forward and reverse directions. When the forward rate equals the reverse rate, a dynamic equilibrium is established. By the end of this lesson, you will define dynamic equilibrium, state and apply Le Chatelier's principle, explain the effects of changing concentration, temperature, and pressure on equilibrium position, write equilibrium constant expressions, Kc, and apply equilibrium principles to industrial processes. Let us begin. A reversible reaction is one that can proceed in both the forward and reverse directions. We represent this with a double arrow, A plus B C plus D. In a closed system, as reactants A and B are consumed, the forward rate decreases. As products C and D accumulate, the reverse rate increases. Eventually, the rate of the forward reaction equals the rate of the reverse reaction. This is dynamic equilibrium. Dynamic, both forward and reverse reactions are still occurring, but the system is not static. Equilibrium, the concentrations of all species are constant, not equal, the system is not at rest, but concentration is not changing. Key point, at equilibrium, concentrations are constant, but not necessarily equal. The color change in NO2/N2O4 equilibrium demonstrates this beautifully. In a sealed tube, brown NO2, nitrogen dioxide, converts to colorless N2O4, dinitrogen tetroxide 2NO2, N2O4, In a sealed tube, the brown color fades and stabilizes at an equilibrium color, not colorless, not all NO2 converted, and not darkest brown, not all N2O4 decomposed. Conditions for equilibrium: the system must be closed, no exchange of matter with surroundings, temperature must be constant. Le Chatelier's principle, Henri Louis Le Chatelier, 1884. If a change is imposed on a system at equilibrium, the system will respond by shifting the equilibrium position in the direction that opposes the change, in order to re-establish equilibrium. Effect 1. Change in concentration. Adding more reactants shifts equilibrium to the right, towards products, equilibrium shifts to consume the added reactant. Removing product shifts equilibrium to the right, system produces more product to replace what was removed. Example, N2G plus 3H2OG, 2NH3OG. Adding more N2 shifts equilibrium right, more NH3 is produced. Effect 2. Change in temperature. For an exothermic forward reaction, an delta H negative increasing temperature shifts equilibrium to the left, reverse direction. The endothermic reverse reaction is favored to absorb excess heat, yield of products decreases, K decreases. Decreasing temperature shifts right, more products formed, K increases. For an endothermic forward reaction, an delta H positive increasing temperature shifts equilibrium to the right, more products, K increases. Rule: temperature change affects the equilibrium constant K. Effect 3. Change in pressure, for gases. Increasing pressure shifts equilibrium towards the side with fewer moles of gas. Decreasing pressure shifts towards more moles of gas. Example, N2G plus 3H2OG, 2NH3OG. Left side has 1 plus 3 is equal to 4 moles of gas, right side has 2 moles. Increasing pressure shifts right, more NH3, fewer gas moles, so pressure decreases, opposing the change. If moles of gas are equal on both sides, pressure change has no effect on equilibrium position. Note: pressure change does not affect Kc. The equilibrium constant Kc is defined at a fixed temperature. For the general reaction, A plus BBCC plus DD. Kc equals C D divided by A B, square brackets represent molar concentrations at equilibrium. The exponents are the stoichiometric coefficients from the balanced equation. Important: Kc changes only when temperature changes. Changing concentration or pressure shifts the equilibrium position but does not change Kc. A new equilibrium is established with the same Kc at the same temperature. Worked example: for the reaction H2OG plus I2OG, 2HIG. At equilibrium, equals 0.1 mole/dm3, equals 0.1 mole/dm3 equals 0.6 mole/dm3. Kc equals Kara2 equals 0.6 Kara2 or 0.1 by 0.1 equals 0.36/0.01 is equal to 36. Since Kc is large or much greater than 1, the equilibrium lies to the right, products are favored. If Kc is much less than 1, equilibrium lies to the left, reactants are favored. If Kc is approximately 1, neither side is strongly favored. The Haber process manufactures ammonia from nitrogen and hydrogen, N2G, plus 3H2G, 2NH3G, delta H equals minus 92 kJ per mole exothermic. This is the most important industrial chemical process in the world. Ammonia is the basis of nitrogen fertilizers that feed approximately half of the world's population. Urea, Nigeria's most important fertilizer, ammonium nitrate, and ammonium sulfate are all made from Haber process ammonia. Nigeria imports most of its ammonia-based fertilizers, a major economic issue. Optimum conditions chosen by Le Chatelier analysis for highest yield, thermodynamic consideration, low temperature, shift exothermic reaction rate, more NH3, but this is too slow, high pressure, more gas moles on left, so shift right, more NH3. For acceptable rate, kinetic consideration, higher temperature increases rate even though it decreases yield. Compromise conditions, temperature approximately 450 degrees Celsius, compromise between rate and yield, gives acceptable rate without too much loss of yield, pressure approximately 200 atmospheres, high enough to shift equilibrium right and increase rate, higher pressure requires more expensive equipment and is more dangerous, catalyst, finely divided ion with promoters, Al2O3 and K2O, lowers activation energy, allows acceptable rate at 450 degrees Celsius without needing even higher temperature. Yield of NH3 at these conditions is only about 15 to 25% per pass, but unreacted N2 and H2 are recycled back through the reactor. The contact process, manufacture of sulfuric acid H2SO4, and the Ostwald process, manufacture of nitric acid HNO3, are also important examples of equilibrium-based industrial chemistry tested in WAEC. Key points: dynamic equilibrium, forward rate equals reverse rate, concentrations constant but not equal, system is not static. Le Chatelier's principle, a system responds to oppose any imposed change. Increasing concentration of reactant, shifts right. Increasing temperature, if exothermic forward, shifts left, decreases yield, decreases K, if endothermic forward, shifts right. Increasing pressure for gases, shifts toward fewer moles of gas. Only temperature changes Kc expression, products concentrations to power of coefficients divided by reactants. Haber process, N2 plus 3H22 NH3, 450 degrees Celsius, 200 atm, ion catalyst. WAEC questions on equilibrium require writing Kc expressions, calculating Kc from data, applying Le Chatelier to predict shifts, explaining Haber process conditions. Always state Le Chatelier's principle when explaining equilibrium shifts.